Today we're going to look at how our area approximations for the area underneath the curve using rectangles can be utilized to come up with an exact value for the area underneath the curve. So what I've drawn here is some function f of x. In this case, that f of x is the interval that we're looking at here from x naught to x sub n, or from a to b. I call this starting point here a, and also x naught, and the ending point b, and also x sub n. Okay. So we're noting that that's always positive here, but that doesn't always have to be the case. This function could always be negative, or this function could sometimes be positive and sometimes be negative, just using the always positive case to make it a little bit easier for us to look at. And we know that if we were to approximate this area using a midpoint rectangular approximation, it would look something like this. We divide it up into some subintervals from x naught to x1, and from x1 to x2, and so on, all the way down to the end. And those intervals could be either equal subintervals or they could be unequal subintervals. And in this particular case, we're taking the route where we're having unequal subintervals. Now, later on, we'll do it with equal subintervals as well. But all we've done here is drawn a bunch of subintervals. And at the midpoint of each of those subintervals, we've drawn a rectangle with a height that stretches up to the function at the midpoint of that subinterval. So, for example, c sub 1 right here represents the midpoint between x naught and x1, and we've drawn a line up to the function there at c sub 1, and we've got a rectangle. We've done the same across this entire thing from A to B. And so the first question we want to ask ourselves here is, what is the area of some arbitrary kth rectangle? So if we're talking about the kth rectangle, I've kind of got one sketched in here where I call x sub k minus 1 and x sub k. That's the kth rectangle. And we've taken its midpoint, c sub k. And, well, the area of that should just be the height of that rectangle, which would be f of c sub k. And then the width of it would just be the change in the x value in the kth subinterval. So f of c sub k times delta x sub k should be a value for the area of that kth rectangle. And now we've got values for our intervals from x naught to x sub n, which means that if we wanted to then find, let's say, the total area underneath this curve, or an approximation, we'd have to add up all of these different areas of these different rectangles. So if we're looking for an expression for the total area, that should be a summation from k equals 1, in other words, from the first rectangle to the nth rectangle of f of c sub k, the height of the rectangle in whichever k we're in. K equals 1 would be the first interval, k equals 2 the second, k equals 3 the third, and so on. All the way to the end, so to n. And then we multiply that by the change in the x value for each subinterval. So delta x sub k. And so this should be a summation, just like what we did last time with the summations of our areas, or summations of our numbers, to represent the total area underneath this curve, or at least a pretty decent approximation of that area. And so what we then want to think about is, how can we make this approximation more accurate? Right? This sum, this area underneath the curve of sum from k equals 1 to n of f of c sub k times delta x sub k. How can we make that more accurate? Well, one way would be to give ourselves more subintervals, or to shrink down the length of each of those subintervals. And because the smaller the subinterval, I'm going to write this on here, make smaller subintervals, right? Make smaller subintervals. If I have smaller subintervals, if we go back to the picture again, the smaller the subinterval, the less we are missing, or the less we are going over our actual area from the curve on each of our subintervals. So the little chunks that are hanging out over the edge, or the little chunks that we're missing underneath it, are going to become smaller and smaller and smaller the smaller we make each of these subintervals. Okay? And so we'd like to get as many smaller subintervals compacted into this partition of our function. And so that's going to be our goal, is to give ourselves smaller subintervals so we can get a more accurate representation. And effectively, what we're going to do is we are going to allow the largest of our subintervals, and the largest of our subintervals is it's known as the norm of the partition, and it's denoted here as this P with double bars around it. That's the norm of the partition. Let's write that here. This is our largest subinterval. We noted that we did have one that happened to be the largest subinterval. So we want to make that largest one tend towards having a width of 0. If we can make the largest one have the smallest possible width, that would mean that all the other ones will also be tending towards having a width of 0. And so if we can make the width of each subinterval equal to 0, then that would mean that there should be nothing hanging out over the edges, or there should be nothing that we're missing underneath the area of that curve. And we should then be able to get an exact value for the area under the curve. Now we'll note here that this is a little bit of a mess. We've got a limit with a norm of a partition approaching 0 of a summation of k equals 1 to n of f of c sub k times delta x sub k, which is a whole lot of different variables and things for us to deal with. And there's not really any real reason why we would need to have a largest subinterval. For any function that we draw, we should be able to have each of our subintervals in our partition be the same length. And if we were to do that, we eliminate this need for us to have a norm of the partition. We can just say, let's let the number of subintervals approach infinity. And if we do that, saying that each of the subintervals have the same width to them, that means our delta x sub k value is no longer going to need that sub k on it. It's just going to be the width of each of the subintervals. And so that's what we're going to do here, is we're going to change that limit from a norm of the partition to being a limit as n, which is the number of subintervals. We're going to let that limit as n approaches infinity of our sum of f of c sub k times delta x. And we'll note that delta x should become b minus a over n, noting that b is the endpoint minus a, which is the starting point of our interval, divided by the number of subintervals. Abbreviate that there. And so in this way, we're now going to have subintervals of the same width. We don't have our norm of the partition anymore. And we're just going to divide it up into equal subintervals and have an infinite number of them. Now, we can't obviously have an infinite number of them, but we can look at what value this tends toward as n goes towards infinity. And that will then give us an exact value for the area underneath the curve. And that right here is exactly what we call a definite integral. It's the value, the exact value for the area under a curve from A to B. And this is the notation that Newton used when he was doing integrals and finding areas under the curve back when calculus was first being developed. And then as we've moved through the years, we've actually started using what's called Leibniz's notation for a definite integral. This one over here on the right-hand side. This is Leibniz's notation, and Leibniz and Newton were both developing calculus at the same time. And this one's a much simpler looking notation. And we call A the lower limit, B the upper limit. And then this little stretched out looking f thing here in the equation or in the expression we've got there is just called an integral sign. And then the thing inside of it, the f of x, is called the integrand. And so we can think of that dx that's at the end is that it's basically the same as this delta x that we've got here, where delta x was the length of the subintervals, and dx is the same thing. It's an infinitesimally small little bit of x. Just like when we were doing differentials in the derivative unit, we thought of dx as just a small change in the x value. That's all it is here. So what we're looking at here is we're saying, let's sum together. That's what this integral sign is essentially meaning. Let's sum together our function, f of x, times the width of the subinterval that we're looking at, that tiny little change in x. And this will also give us a value for the exact area under the curve once we actually know how to, mathematically take an integral, which we'll learn quite soon. So a is the upper limit. I'm sorry, a is the lower limit, b is the upper limit, and f of x is called the integrand. We need to be able to convert back and forth between these two notations because on the AP test, they will often ask you in one of the multiple choice questions to do this. Usually, it's having us go from a Leibniz notation, which is the notation we're going to be really used to, into Newton's notation. And that's what we're going to look at next time. But on rare occasions, they also have you convert from Newton's notation into the Leibniz notation. So we'll do one of those things, and that'll be enough because those are pretty straightforward. And then next time, we're going to take a look at how to convert from the Leibniz notation into Newton's notation. And then even how to evaluate it once we have it in Newton's notation. So here we are saying that the interval from -1 to 3 has been partitioned into n subintervals of equal length. We've got c sub k is the midpoint of the kth subinterval, and we want to express this limit, the limit as n approaches infinity, of the sum from k equals 1 to n of 3c sub k squared minus 2c sub k plus 5 times delta x as an integral in Leibniz's notation. So the first thing we know we're going to need is an integral sign. And within that integral sign, we just need our function. So this will be our f of x, except instead of writing c sub k squared, because we no longer care about the midpoints of it, we just care about the function itself. It'll just become 3x squared minus 2x plus 5. And then the delta x is effectively just our dx, that infinitesimally small piece of x. And then we still need a lower limit and an upper limit. And if we just look at our Newton integral here with the limit and the summation, we won't know what values to put there. We have to actually go back into the problem and read what it's talking about. It's telling us that we have an interval from -1 to 3 that's being partitioned. So our lower limit will be -1, and our upper limit will be 3. And that's our integral in Leibniz's notation. And effectively what this is saying is this, or what this expression is it's equivalent to the exact value of the area under 3x squared minus 2x plus 5 underneath that parabola from x equals -1 to x equals 3. And on rare occasions, they might ask you to do this in the multiple choice on the AP test. More likely, though, they'll have you go the other direction from a regular integral in Leibniz's notation into a limit with a summation. And so that's what we're going to work on next time, is turning these integrals into limits and summations and seeing how this really works behind the scenes before we develop some really convenient, easy rules for taking integrals and finding exact values for area under the curve. But for today, that's going to be it.